Hello everybody and welcome to OptiWave's webinar on optical sensor design using OptiSystem. My name is Brian Tipper. I'm the VP of Sales and Marketing here at OptiWave, and I'll be sitting alongside your host Philip Wheatman. Before we begin, let's quickly review the layout of today's webinar. During the presentation, we're going to launch 3 polls, such as the one that you're viewing now. Each poll provides Philip with helpful feedback for guiding the presentation, so your participation is greatly appreciated. We will also handle questions at any time during the presentation, but via the questions section only. You'll find the questions section in your GoToWebinar control panel. Please note that since we have a full house today, we won't be taking any questions from participants with raised hands, as we don't have sufficient time to pass mic control back and forth. So again, if you have a question, please type it into the questions section. And in the case where you wish to keep your question completely private, you can send it to support@optiwave.com and we'll handle it at that point. If for some reason we're unable to handle your question during the webinar, we'll jot it down and reply to you afterwards via email. Also, in the GoToWebinar control panel, you'll notice that we have 4 handouts available. Please feel free to download these handouts at any time during the presentation. Lastly, we will be recording this webinar and distributing it to all registrants via a download link that you'll receive in an email tomorrow at this time. In order to access the recording, you're going to need to use the same name and email that you used for the webinar registration. So without further ado, I'd like to introduce your presenter, photonics research scientist, Philip Wheatman.
Hi everybody, this is Philip here. So today I wanted to talk to you about using optical sensors in OptiSystem. I think there's no people who have experience with OptiSystem, but they usually associate it just with doing communication simulation. So today we wanted to show you that you can actually use it for sensing as well. So a brief outline. We'll talk about how you can do optical sensing with OptiSystem and what would be the use of it. Next, actually, I want to announce that we want to solicit some opinions from everyone here as further directions to develop our sensing capabilities. And then finally, we'll go through some examples to show you sort of the basic ideas of what we can do with OptiSystem and sensing. Okay, so as you can imagine, when you've got an optical signal, there's various things, characteristics of that signal that you could use for sensing. The phase, the frequency, the amplitude, or the time delay of an optical signal. In an OptiSystem, of course, we simulate these signals, so you can use these various characteristics for sensing. And so we can design with our current components a number of different simulation systems, and we can also, in some cases, we use some co-simulation, which I'll talk about. And the reason why I think OptiSystem would be is a very useful tool for this is because often, I mean, there's a number of software devices, designers you can use to simulate how an actual device could do the sensing, but there's not very many that would actually help you simulate how it would actually work in a whole system. For example, is the atmosphere the way it is right now, is this, would this provide too much interference or attenuation for the actual sensing that you want to do? And so system is a good way to analyze this, and I'll show you in the examples that we have why I believe this is so. So before we get into it, first some solicitations. We are very interested in hearing from anybody on any ideas they have on sensors that they would like to design, because we desire that OptiSystem will expand more in the optical sensing regime. So as you go through this, as we go through this talk, I want you to think about how this could apply to some of the designs that you have, whether in just building a system from what we have as existing components, like, for example, with the LiDAR or our fiber optic gyroscope, or in fact even new sensing components, such as our most recent fiber Bragg grating sensor. If you have any ideas, we'd be happy to hear from you. Okay, with that out of the way, let's get into a few examples. So the first one I'm going to talk about is LiDAR, which is light detection and ranging, so laser rangefinders basically. And we've going to show various designs using using the time of flight of a laser pulse, using the phase shift of the light coming in, as well as the frequency, changes in frequency with the frequency modulation continuous wave. So you may not be someone who is researching LiDAR yourself, but we hope that with this example you'll see some of the basic techniques that you could actually use for sensing with OptiSystem. So first one with LiDAR is you just simply using the time of flight. So basically all you do in this case is you send out some sort of Gaussian pulse. It travels through your atmosphere, gets reflected back, and then when it comes back into your photodiode, you detect it, and essentially from the delay of the signal, you can tell how far away your object was. Basically just distance over time. You see there's a factor of 2 in this time of flight times the speed of light over 2, just because it went back and was reflected. The term below is our model for various atmospheric distortions. So it's a very simple idea. How long does it take for a pulse to arrive? Now, put it in practice, it's slightly more complicated because you have to be able to trigger your device to be able to sense when the pulse has come in. And so there's various techniques that have been developed for this, and the one that we're using here is called the constant fraction discriminator. And you can see it in this graph at the bottom right. You essentially, what you do is you copy your pulse, you flip it over, give it a little bit of a phase shift and change the amplitude, and then the triggering of this pulse is actually where it crosses 0, and it tends to be much more robust in terms of noise. So it's better for determining when the pulse is received. So that's just using a time of flight. In the next example, here it is using the phase shift. So in this case, what you do is you send your signal out and you actually give it a modulation. As you can see, we've got an amplitude modulator there. So we have this amplitude modulator. So we send it out at a certain modulation, and when it comes back, then we can tell, comparing it with the initial reference signal, the phase shift between the two. So there's lots of techniques that are used for when you want to use light for distance measurements where you're using a phase shift, like a Michelson interferometer or something. So it's that same basic idea. Now, so you get this phase shift, and from that phase shift, then you can calculate the distance, as you see here. So this calculation here is actually done in, you see this component right at the left, it's called the C++ component. And we actually do the calculation in here. So this is a custom component we design. Incidentally, for those of you who have used OptiSystem before, I think many of you are probably familiar with the fact that you can co-simulate with MATLAB. In fact, we also have a C++ capability now, which has been in there for about a year. It's a little bit more of a learning curve, but the C++ is actually much faster, and once you get used to it, it's actually quite easy to use. It's much faster. They run at the same speed as any of our native components. So I would encourage anybody to take a look at that. And as well, it's actually free, too. So you don't have to pay for something like MATLAB. In our next version of OptiSystem, we're also introducing a Python component. So you could have done any of these in your custom component there. So that's how you would do it with a phase shift. This technique here is called the frequency modulation of a continuous wave. And so the idea here is to use the frequency, a change in frequency. So you send out your signal here. So you send out your signal, and it's actually, this has got a sawtooth waveform generator. So the reason why I use a sawtooth waveform generator is because it's predictable what kind of frequency components you'll get out. So then what happens is you send your signal out with the sawtooth waveform generator. It goes through your system and it comes back, and depending on how long it takes to get back, this component will mix with a different frequency component from the sawtooth wave generator. It'll create a beat frequency somewhere, which you see over here in the figure where we've got in this square. So you've got this beat frequency, and from the knowledge of that frequency, you can actually calculate what the distance is. And so we have the equation here. Here's your beat frequency right there. So in this case, you have to be careful with how you adjust the ramp time of your sawtooth generator for the appropriate distance that you want to measure. So this would be a good use of OptiSystem to determine, okay, what is the best ramp time to use, what kind of atmosphere can we have where this will still work. And again, we've got our custom component, we wrote a C++ component to be able to convert from this frequency to our distance with this formula. I see we have a question about how to interface MATLAB in C++ with the simulation in OptiSystem. We have a number of tutorials online about how to do that. So if you go to our website, you will see these tutorials. In fact, we've got especially for the C++, because it's a little bit more complicated to use, we have a whole 60-page tutorial on it, as well as we have a number of different examples that you can download and try out so that you get a hang. Once you get used to it, it's actually not too bad to use. Okay, so that was the LiDAR. Another example we can show you is with the fiber optic gyroscope. So the idea behind a fiber optic gyroscope is you've got a loop of optical fiber, so you could have multiple loops actually, and the light is split and sent clockwise and counterclockwise through this optical fiber. If the loop is rotating, due to a Doppler shift, you're actually going to induce a phase shift between the two different paths of the light, so that when you recombine them, you'll be able to measure this phase shift and therefore calculate the angular velocity. So we'll show two methods to use this. One is called the DC method, which is a little simpler, but it's you can't use it very well for low speeds because there tends to be a little bit too much interference for the speeds to be accurate below about 1 milliradian per second. So it's for a bit higher of a speed. You also can't determine the direction, and you can actually see that from this equation, because when you pass the light through, so here's a schematic of it. You send out your light, it goes through your coupler, and you see the light, part of it will go through a clockwise and part of it will go through a counterclockwise direction. And then when you come back through the coupler, then they're coupled together, and then you detect them in a photodetector, and by the phase shift you can determine the speed. And so you see this first line, we've got this equation here for how you can determine this phase shift. So the I is the current that you would measure in the photodiode. The I naught is the current if you had zero speed, which we can calibrate the system originally, or what you could do is you could measure it at zero speed if you like. And then this phi s is your phase shift, what they call the Sagnac phase shift. And from that phase shift, then you can calculate what the actual speed, and that's this capital omega in this second equation. And what you notice is by this equation for the Sagnac phase shift, you see it's a cosine of the phi, which means cosine of plus phi or minus phi is just the same. So that's why you can't tell what the actual direction is in this case. Oh, we also have a question of which version of OptiSystem is C++ included. I believe it's started with 14.0, so it's available now. Okay, so this is using the DC method. Here is a phase modulation method. So it's a little bit more complicated than the other case, but it tends to be much more accurate. So what we do instead in this case, and let me go back to this spotlight. We send the signal out through here, and you see when it gets coupled, it's split, and it goes again in the clockwise and the counterclockwise direction. But notice that we also have something here called the PZT phase modulator. So that's piezoelectric phase modulator. So what that will actually do is it's piezoelectric, so it's going to slightly change the size of the, it's going to induce a strain on your actual fiber. So that'll mean that the path of the light will change slightly. And so this is at, you modulate this at a certain frequency. And notice that the clockwise or the counterclockwise, when it goes through the phase modulator, it's right at sort of right at the beginning of the loop. Whereas in the clockwise, it has to go through a number of loops first before it actually hits a phase modulator, which means that they're both hitting this phase modulator at different times, and therefore they both get a slightly different phase shift. And then once you do that and you recombine the signals and go into the photodetector, you can actually get a relation between this I over I naught. So I again is the current that we measure, and I naught is the current at zero speed. So because of this modulation at this frequency, you actually will get a signal that looks like this long equation at the bottom. Now, the first term, which would be the zero frequency, is just this one, the J naught phi m, the 1 plus J naught phi m. And that is actually the DC value that we had before, whereas the J naught is your Bessel function, the first Bessel function. And so this actually becomes the DC value. The second frequency component, and this is what we have in this rectangular box here, and this is the one we actually use. And that's determined from the second term. You see that it's the K is equal to 1 term here. So when you have the K is equal to 1 term, you'll get out the first frequency component. And that's the one we actually use for to measure our phase shift. And I'll show that on the next slide. So here is your phase shift, right up here. So this is the very first frequency component. Now you notice that it's a relationship with sine of the phase shift. So therefore you can determine the actual direction that this object is rotating, clockwise or counterclockwise. This tends to be much more accurate than the DC version. In fact, we can go down to about times 10 to the minus 6 radians per second with this device. And so here's our simulation of it below with OptiSystem. You see here's our phase modulate. So this simulates our piezoelectric modulators here, and here's your phase shift going through the system. And what we've got another C++ component here, and what this component does is it takes in the current, this one here, and it rearranges this so that we can find our Sagnac phase shift. And if you recall then, once you've got that phase shift, then you can find your angular speed. So our C++ component back down there is the one that will do all those calculations for you. And it's about 10 or 12 lines of code in our C++ component. So it's not very difficult to make them. So that's it for our fiber optic gyroscope method. I just want to post a quick poll before we go on to showing you one of our newest sensing components. And while we do that, I will actually So while we set up the next poll, I've got another question here knowing, can we simulate phase OTDR system with direct as well as coherent detection? I think we can. Once you give us, send us an email and we can talk about it, but we should have all the basic components for that. Okay, so let's go on to our next next slide. Okay, so that was the end of our fiber optic gyroscope. So let's talk about one of our newer components. We introduced this one in OptiSystem 14.20. We've had some updates that will come in 15 for it to make it even more useful, which I'll talk about when we get to one of the examples where I actually use them. So the basic idea between the fiber Bragg grating sensor is that in a Bragg grating, the temperature and the strain will affect the wavelength and transfer functions. And you can imagine this because what happens is the temperature or strain will change the size of your grating. And therefore, if you're changing the size of your grating, then you're also changing the wavelengths that can get through or reflected. And we show them down here, the basic equation. So here is your reflection and your transmission. And these depend on your coupling strength as well as your phase mismatch. And the main relation is the one that I've got in this box here, which shows how the wavelength of your Bragg grating changes as a function of strain and its temperature. And you see we've got these coupling coefficients in here. So this is how, if you know these coupling coefficients, and then if you've got a strain or a temperature change that occurs, then you'll be able to measure this change in wavelength, and therefore you'll be able to tell exactly how much this strain or temperature change there was in the system. So the first example I'm going to show is actually one that we include in our samples file. And I'm going to go through this actually from in our OptiSystem. Okay. So if you go into, so take a look what I've got right here. Okay. You see this path I've got, it's documents, OptiSystem samples, and if you go into the folder sensor systems, we have a number of examples in here, and the one that we're looking at, so here in fact are the LiDAR examples and the fiber optic gyroscope. And if you go into the fiber Bragg grating sensor, this is where this example is here. This example, I've got 4 gratings. So this is the one I'm going to show you for a minute. I've already pre-run this example. So what we have is 4 different grating sensors. See, we've got 4 different sensors here, right? And what we've done is the first 2, we've set them so that they only measure temperature. I don't know if you can see this. It says temperature effects yes on here, and temperature effects yes. And we've got some temperature, and this is actually a linear change in the temperature that I'm showing here, and I'll explain how that works in a minute. For the third and the fourth sensor, these are actually located at the same position. You see what happened here? This one is a temperature. This sensor here has a temperature effects. You see it's yes there. The second sensor here has temperature effects as well as strain effects. Now we put these both in position 3. Now you may wonder why we're using 2 there, and I'll show you that. Let me just go back up to this slide. Let me go to the previous page here. Okay, if we go to this equation that we've got here, because it's basically, we're going to be using this change in the Bragg wavelength. You notice that it affects both the strain and the temperature. The problem is, you can think of it as an equation of 2 unknowns. And so therefore, in order to be able to solve for both of these, you essentially need to have 2 changes in wavelengths. You need to have 2 equations and 2 unknowns. So what normally researchers will do, if they want to measure both the strain and the temperature, is they'll put 2 gratings in one spot, and one of them they will leave a little bit loose so that it doesn't actually feel any strain effects. And essentially that one becomes a temperature sensor. And then once you've got that temperature from that first grating, then you can use that as an input to the second grading. So that's the idea that we've got here. So this sensor is only measuring temperature, and then once you've got the temperature from that one, then you can use that as an input for here, and then this one can essentially measure the strain. So so you notice they're both at the same position. Now, in order for you to be able to use this, you also have to have what we call the interrogator. You notice I've got something here called an interrogator. I've put one on both ends. Temperature and strain measurements usually would happen every second, maybe every millisecond. But as you're aware, when you're in the optical regime, you're normally working on the order of nanoseconds. You can't simulate a system for a number of seconds if you have to have some sort of time division on the order of nanoseconds. So what is normally done is you have an interrogator, and what this does is it will say every second it'll send out a stream of optical signals, it'll pass through the system, come back, and then a second later it'll send out another stream, pass through and come back. So you're essentially interrogating the system every time step, whatever you choose. In this case we chose every second. So that's what the interrogator function is. And these are actual real devices that are used in industry. You can find a number of companies that actually build these interrogators. So let me just take a look at this fiber bright grading sensor here. Oh, we have a question. Is the interrogator equivalent to an optical spectrum analyzer? Actually, often people will just use an optical spectrum analyzer for the interrogator. And our interrogator is a modification of our spectrum analyzer. It does all the spectrum analyzer functions, as well as it performs our extra calculations, which I'll talk about for calculating the strain and the stress. But I think if somebody can't afford an interrogator, but they already have spectrum analyzers, they'll use that, and at every interrogation step they'll measure the frequencies, and then they'll have to do a calculation externally on that using those values for the stress or the strain. So we decided to combine it so we could actually do the calculations within our analyzer there. So what I've opened up here is the Bragg sensor, the very first one there. And if you notice here, it says the original Bragg wavelength is 1545 nanometers. So this is a sensor that's been set at 1545. That's the original. If I go back to here, so that would be the lambda b at the bottom of that equation. And we've set this up so it's essentially a Bragg filter, and you can either define it by physical parameters or by some effective parameters of bandwidth or reflectivity. It's up to you. So we've set this one again at the 1545. Now if you go into the sensing parameters here, you see that I've checked for temperature effects. So this one is being used as a temperature sensor. I haven't checked the strain parameters. Now in this case, you notice that there's it's written in orange, it's temperature, and you see how it's written as 2 times interrogation index plus 20. So this starts at 20 degrees, and we actually have this scripted to something we call interrogation index. And if you take a look on our layout, here's our interrogation index. And we've got it scripted, so what it's going to do is the interrogation index is going to sweep from 0 to 19 by steps of 1. So what that means, then, if you go back into here, so the interrogation index starts at, the first value is 0, so this is going to start at 20 degrees, and then it's going to, this interrogation index is going to increment up by 1, up to 19, so that'll be 58 degrees is what this thing will end at. So that's the first sensor. We have a question. Can we sense more parameters other than temperature and strain? That's a very good question, and in fact, I encourage you to stay to the end of this presentation as I'm actually going to be talking a bit about that. So, so this is the first sensor. Again, it's at 1545. The second sensor is very similar to the first. It's for temperature. But now, if you notice, the original Bragg wavelength is at 1550. In this sort of system, you have to have each sensor have its own distinct original Bragg wavelength, because you want to measure the shift on each sensor. If they were all at the same Bragg wavelength, as you notice that the signal is passing through all of them, it wouldn't be able to make sense of which sensor is actually shifting. So you have to make all of them at different Bragg wavelengths. So this one, and this is what is actually done in practice too. So the second one's at 1550. The third one here, you see it's at 1555. And if you go back into the sensing, now just as a demonstration, I decided instead of having this one indexed to that interrogation index, instead I've loaded an external file. I call it, this is temperature.dat. And this is just a file. It's got 19 numbers in it for represent different temperatures. Just to show you that you can either script that temperature, or you can actually, if you've got some, say, some experimental temperature measurements you want to use to try out, you can use those instead. Then finally, the fourth one, and this is the one with the big difference, is it's at 1560, so again, its own Bragg wavelength. But you see this one now has temperature as well as it has strain. You could use stress parameters instead if you like it, and it'll internally convert it into strain. It's up to you. So you see it's got the temperature. It uses the same temperature file as the previous one, which should seem reasonable because they're assumed to be located at the same position, so they should feel the same temperature. But now we've also got strain effects, and this strain zz.dat file is just a data file that's got a number of strains in it. So that would be how you set up your sensors. Now, as I mentioned, you need an interrogator. The interrogator has to know what all these different wavelengths are. You noticed that I had each sensor was at a different wavelength, so the interrogator has to know that. So if you actually look at our properties, okay, if you go into the second one for the sensing, what you notice is I've listed them all again. Here's all the sensors, sensor 1, 2, 3, 4. 1, 2, and 2 are at their own positions, 1 and 2. See, I also put in their wavelengths, 1545, 1550, as well as their temperature. You see that the E is N, that means that there's no strain. Sensor 3 and 4, you notice, are at the same position. They've got their own wavelengths. Sensor 3 is just temperature, and sensor 4 is the temperature and strain. So we've just told the interrogator what our system looks like there. I've also got an option up here. It says use spectral maximums. There's also an option for minimums, and I'll show you why you would change that in a second. Okay, so I've already run this. So if you now you double click, so it'll look just like our optical spectrum analyzer. So here's all the signals as they've gone through. Okay, so this one is measuring the reflectance. So here's your reflected signals, and remember I said there was an option for use maximums. So that's where you'd use your maximums, is right here. If you take a look, I put an interrogator on this side. It has the transmissions. Okay, so you see that this one had reflected maximums. The transmissions are the dips. So in this case, you would have to use minimums to determine where your how your wavelength is changed. So as you move through the system, you will actually see this wavelength change. But before I show you that, if you go into our project browser, and so here's the first interrogator, and let me show you this. If you come back down here, here is the strain for position 3, and in fact this is essentially what I put it in as, so you can see how the strain changes. And let me show you the temperatures at each of these positions. For the first two, I just had it linearly increasing. And then for the last two, it was, again, it looks something like this. Now you notice it's not perfectly straight, but, and I actually did this on purpose to demonstrate using OptiSystem to simulate this. So you can get it to be a much straighter line depending on what kind of sampling rate you chose and what kind of noise there is in your system. So this would be something that would be useful for OptiSystem, so you can determine determine what would be the optimal configuration. Oh, can it model cross-sensitivity? We have a question about, can it model cross-sensitivity between strain and temperature? So, as I've mentioned before, the only way you can essentially decouple it is by some sort of configuration like this. You could actually have each one of these have different, both be able to take temperature and strain effects, but then your coupling parameters would have to be different in each of them, which is a little more complicated. Mohammed, I see you've got a question. This one is fairly complicated, so why don't you send us an email afterwards and we'll talk about it then. Okay, so there's how your system would perform. Now watch, I'll show you as I watch what happens to the peaks in this interrogator as I go down by sweeps. Let's see if I go down here. Maybe you can see that. Can you see that it's shifting slightly? And it's that shift that we're measuring. Okay, so that's basically how our sensor and interrogator will work. Okay, so that was the system. So you could imagine putting these sensors, you can assume that, imagine that you're saying you're located at different sections of a bridge, for example. And there's that same figure. Now, this is a second example, and this was in fact from a graduate student it was the start of why we decided to start improving our sensor capability. And here's the design. It's a rather interesting design. So you send in a light signal if there's communications that you're trying to send both ways. And what happens is that this is the normal channel. The top channel is the normal channel, and it's got a fiber brag grating in there. And if this fiber brag grating determines that the bridge, there's too much strain in this bridge, then it will actually switch to the secondary channel below, and this is a free space channel. So what we're going to look at here is this section up here, the fiber brag with the fiber brag grating. Now this one presents a few complications compared to the previous one, and I'll show you that here. So here we've set up this system. So we send our light in, and we've got over here we've got some WDM transmitters, and we send the signal through. It goes through a fiber, and it goes through. Here's our fiber brag grating sensor, and see it goes through here, and it uses part of the white noise from your amplifier as your strain measurement, and you can see it looks nice. You got a nice peak that comes out right here. Okay, but the problem is that's not where you're actually going to be able to do the measurement. The measurement happens after it passes through a fiber again, and it comes down to what I call the fiber brag grating detector. But you see what happens is, look at where this amplitude is, around minus 60 dBm. Once it's reflected and it passes through this, it's added to this transmitter. So what you're actually going to measure is out here. Now you take a look, you see where the amplitude is. It's much smaller. So if we went to, so this is at a certain stress level. Now if you go to a second stress level, here, you notice how the position of that peak is shifted, as you would expect with the fiber brag grating. But on the left, which is where we measure it, it's just too noisy to use our interrogator. The interrogator is not going to be able to find a peak of that very well. So we actually use another technique instead, where we essentially filter around that peak. We filter around that peak, and we measure how much of the average energy within that filter. And I'll show you in this next slide how we do this. So here we've created a filter here. It's a rectangular optical filter, and it's centered at the Bragg wavelength, and we got a certain bandwidth. So this is the amount of power, optical power, when there's no strain on it that's within this bandwidth. And you see, as the strain increases, the amount of power that's within this filter decreases. And we've even got it plotted here. So you can see once it's gotten past a certain distance that there is very little power in it. And this is, you could use this as your strain measurements. This is the idea behind this one. How much time? Okay. I'll quickly show you this one more fiber Bragg grating example. Now, in this case, this one actually comes from, and this one I think demonstrates quite well the power of using OptiSystem and the sensor design. This was it's a non-contact interrogation of embedded fiber optic strain sensor. So the idea was that they didn't want to have extra fibers or sensors embedded within the object. They wanted to be able to have the detector separated. And as you can see, they've designed it so that there's an air gap. And in fact, the other picture will show it even better. Let me reduce this a little bit more. So this image on the left, the idea is that you've got your source here. It goes through a single mode fiber. There's some sort of air gap. It gets collected in this with a little mirror. It goes through a multi-mode fiber, spliced onto a single mode and onto our grating, and then it goes through this whole system on the other side too. And so the actual measurement is done here. So you see it's not contacting the surface at all. So the question is, can you actually model, could you actually get useful stress measurements out of a system like this? And so this is a good case for OptiSystem because when we can test some of these conditions. So here I show you what this actually looked like in our system. Let me just minimize this for a second. Okay, so you can see coming down on the left side here, this is modeling this part, and it comes across here, and then it comes back up to the other side. So here I show you two examples, and in this case we've got there's that gap, the air gap between the actual sensor and the object is 1 millimeter. And you see, in this case, yes, we can measure a strain in there. You can see that the air gap is small enough that the signal is not overwhelmed by the noise in the system. In the second case, I simulated by increasing this air gap to 2 millimeters, and you see what happens. There's just too much noise, and we can't actually get a signal. So this would be a useful case to model something like this in OptiSystem, because it could tell you, can we actually set up a useful system that will give us some information, or what do we have to adjust in order for this to work? Do we have to increase the power of our white noise? Do we have to reduce the air gaps? Various questions like that. So hopefully that'll demonstrate how you can use our new sensor capability and ask some questions and get some answers for systems like that. Okay, so finally, this is the last topic, and this is what's upcoming in OptiSystem 15. We have a new sensor that we've designed, and this goes back to one of the questions that somebody had about, can we do things other than just temperature and strain? And we've got a new component that you'll see in 15, which is called a measured sensor. And in this, you can use up to 1 or 2 parameters, and they can be whatever you like. We were thinking of various applications, maybe bacteria detection or gas sensor or bending. If anybody has any ideas for how they would like to use this, we'd be very happy to hear them. So it looks a lot like our fiber bag grading sensor, except for in this case, we don't use the fiber bag grading transfer functions. We actually import your own experimental data into here. So these are what you would do is, and I show them down here, say some transmission and reflection transfer functions. So you'd actually import these in here, and I've done it for 3 different parameters. So for example, these could be the transfer functions for 3 different bacterial densities or 3 different bending strains or something like that. And then what OptiSystem will do with this is for any values that are in between, it'll interpolate between these transfer functions to give you a smooth function. So we believe this will be very flexible for people to use, so they can try it for different sorts of system. If you've got some experimental transfer functions for the type of sensing system you want, we invite you to give this one a try. And again, it can work for up to 2 different variables. Just to give you to demonstrate how it works, what I did was I actually compared it to our fiber brag grading sensor, just to show that it gives the similar results. And in this case, here was for your fiber brag grading, what your transfer function actually looked like, and I just cut out a section of it and I said this is going to be my experimental transfer function, and I did this for 3 different strains. So these are this section of the fiber brag grading transmission function for 3 different strains, and then what it'll do is it'll interpolate in between. And so I swept a strain for a number of parameters, and you can actually see this is a comparison between the 2 models for a certain increasing in strain, and you see you can actually get some fairly close results here. So this was our way of validating that this measured sensor will actually work, and I've actually done it for 2 parameters, and I did it with both the temperature and the strain effects, and it works, as well as the fiber brag grading sensor. But this is, we hope this will be a powerful tool for people to use to try with whatever kind of system they've got. We'd be happy to hear from anybody if they've got any ideas on that. So that's concludes the presentation. I hope from this you've gotten an idea of how you could actually use OptiSystem with some sort of sensor applications, or as you followed through, maybe it's given you an idea of how you could modify or how you could create some of your own designs for some of the types of systems that you would like. If I didn't get to anybody's questions, please feel free to email us and we can talk about it, especially if you've got ideas for your own designs that you want to try and implement.
And
Thanks very much.
I also wanted to step in and add that both Philip and I are going to be at OFC next week at the LA Convention Center. We're at booth 2947, so if you're in the area, feel free to drop by and let us know what you're working on or any suggestions for the software tools that you'd like to see put in place. So yeah, we'll take all the questions that are remaining right now, and I think the best thing to do is just email everybody individually. So thank you very much for joining us for the webinar. Have a good day.